It's my pleasure to introduce FactSage 8.4 to you now. And then I will give a short demo on advanced use of Equilib. Essentially, I want to, will be probably for most of you rather basic. I have one Easter egg, which is actually advanced use. Everything else is probably rather basic use, but still, I want to introduce a couple of concepts to you. Using a tool that you know, because there are other tools that you don't know yet. And these will be demoed tomorrow. Yeah. Okay, let me start with a short introduction of the databases so updates in databases in FactSage. So this is, as you know, if you go through the what's new in FactSage pages, these are always very long lists that have to be then boiled down. So a few highlights on this slide. So first of all, the FactPure substance database, there are 165 compounds that are added. In the FToxide database, there's an update of the systems that contain potassium and iron oxide, of the systems that contain tin oxides, and on the zirconium and sodium containing systems. The FTsalt database gets two new liquid solution phases. One is covering the sulfates, chromates, and molybdates, as expressed with this complicated way of stating this. So we have A2MO4 and A2M2O7, where A is sodium or potassium and M is sulfur, chromium, or molybdenum. And there is another part describing zinc chlorides, lead chlorides, and mercury chlorides. Then there will be a new database in the Fact Solutions database package, which is dealing with ionic liquids. So the FTionx. I don't want to read out this list of ionic liquid end members, but you can see that there are quite a number of them. These are liquids formed in low temperature liquid phases. These are the cations here, so organic materials. And then there are 6 more anions, making a rather complex and large database. Really a new field in FactSage. Then the FSstel database. The mu phase, if you ever really looked through the list of phases in the STEEL database, in the current version, you would see, I guess, 3 or 4 different solution phases of mu phases. The mu phase is an intermetallic which is really hard to model consistently. And that has been updated now, and the same is also true for the sigma phase. And there's only one mu phase in the new version of the FSstel for all of these rather complex metals. Of course, this is not only interesting for steels, but also for super alloys and for high entropy alloys. And also another significant update is the hydrogen solubility. So I think if you want to model hydrogen solubility in steels, as far as I know, FSstel would be the best database to do that. And there has been an update here on the vanadium-rich side of the BCC solution also. The FTlite database, you can see here from the list of binary systems. This is a rather small update. In other years, these are maybe 100 systems that are added. But still, this is by far the largest database that is available in literature or in the world when it comes to light metal alloys, aluminum alloys, magnesium alloys, but also titanium and even alkali solutions. The FScopp, which is a sister database, gets a very significant update with with over 80 additional binary systems to look up. I mean, I don't have at the top of my head the list of binary systems, but you, of course, if you're interested, you should look this up. Again, this is the largest database available for copper alloys. Then the SGTE solutions database also, that is a significant update as we have seen in previous years. SGTE usually gets updates every 2 years. And then every 2 years, roughly 100 systems are added. A very steady database extension here. So now there are 880 binary systems. And finally, the SpMCBN database. SpMCBN, you can see I don't list binary systems, but ternary systems, because this is a database on silicides, borides, carbides, nitrides. I think most of the binary systems are covered anyway. But then it's important to cover the ternary systems where you have 2 metals and one of the carbon, nitrogen, boron, silicon, or you have 1 metal and 2 of the other. So the ternary systems are really the important ones. And here there is another rather large extension of the SpMCBN database. All right, again, the largest database when it comes to ceramics, so non-oxide ceramic systems. Then a little bit more information on the GTOx database. So we have introduced 1.5 years ago in the last update already a completely new model for the single liquid phase, which we have called SLIC, standing for single liquid. So that is a single liquid solution phase covering slag, liquid metal, liquid salt, all modeled as a single phase, which is far from trivial to do that. It's the first database that does this of this size. We have started this 1.5 years ago. We have completely revised the model, leading to even better extrapolations to higher component systems. In addition to that, we have also added lead and cobalt as new components, both on the metal side, the oxide side, and the sulfides. We now have a near 100% coverage of binary metallic systems, as you can see in this plot. So here you have the now, I think, 19 metals that are in GTOx on one axis, 19 metals on the other axis. And the few black dots are the systems where never any phase diagram has been reported that we could have used as a basis for fitting parameters. Also here you see the assessed binary or quasi-binary oxide systems. Again, a very, very, very large coverage with the small black column that you see here. This is the calcium fluoride, where only a few systems are actually included here. We have also worked extensively on slag metal matte equilibria. So you see here on the right-hand side, partitioning of lead and matte versus lead and slag, sulfur and matte versus lead and slag, and also sulfur and slag. In a 1, 2, 3, 4, 5, 6, 7 component system, and where we are able to nicely reproduce the experiments that have been performed, I guess in this case at University of Queensland a couple of years ago. This is all very important, I think, for non-ferrous metallurgy, and also especially important for lithium-ion battery recycling. So if you're interested in that topic, this is the best database to do this now. Density has been added to all the phases. Again, this has been the work by Abdumonum. So most of the density values that are in the database are estimated databases only for the small subsystem of silica, calcium, iron, magnesium, sodium, potassium oxide, aluminum oxide. This is actual modeling for the density. In total, we have an addition of 220 quasi-binary systems, 66 ternary systems, 20 higher order systems, mainly salts and phosphorus oxide containing systems. A lot of work that has been performed by our good partners at Forschungszentrum Jülich. Thank you, Elena. Okay, outlook for next year. We have started already work on the addition of boron oxide as a new component to GTOx, and we will improve relevant glass systems. Also here, we have a new project in that area. And if you have any requests, then Alex there in the corner is the right person to contact. Okay, good. Then another very interesting topic are the new add-ons. In FactSage 8.4, you will find two new process simulation tools, which are the FactFlow and FactProSim. Now, we will explain you why there are two process simulation tools. This is our mission for this users meeting, because this is probably maybe not ideally or not super easy to understand, but there are very good reasons. So the FactFlow is developed by the group of Professor Jean-Philippe Harvey at Polytechnique Montreal, so our partners at CRCT. And there the focus is on process flow sheeting made easy. So it is a graphical user interface that allows you to connect several equilibrium calculation reactors in the end. We will demo that tomorrow morning, first thing we will do. And then there's the FactProSim that is has been developed by Professor Inho Jung and Professor Maria-Aline van Ende, both at Seoul National University in Korea. And there the idea is to make effective equilibrium reaction zone type of modeling easy by giving you a graphical user interface to set these up. Again, tomorrow morning you will hear more about that. Okay. Good. Let me motivate this, and maybe I will just introduce you now graphically in a graphical manner why and for what purposes you would use one tool or the other, or even ChemApp for Python. So in the last presentation, we have already seen the steel making process, and that is not only one reactor, but you have several reactors. At least you have the converter, and then you have the ladle furnace. And in the ladle furnace, you probably are doing several processing steps. And also, if you go to the EAF route, again, you have several steps that you're doing. Just very abstracted and removing a lot of complexity. We start with the pig iron, so iron containing a lot of carbon for those who are not from the steel business. We first create our first raw steel here, and then we go to the alloying, we do the degassing, and the desulfurizing might be different in different plants, but just in general, these are the steps. And always, of course, the steel is entering the next step. This is, of course, an extreme oversimplification, because not only pig iron will enter your LD converter, but also other materials. So you will add probably scrap, cooling scrap, or DRI. Both the scrap and the DRI will contain other impurity elements. They are not 100% iron, of course. Then you have also lime addition that you do, maybe also other slag formers that you add to the converter process. And of course, you blow in oxygen because you want to use the oxygen to remove the carbon from your steel, from your liquid melt. And also, of course, on the outgoing side, you do not form only steel or raw steel, but you also form a slag or you form a gas phase. Yeah? And that's true not only for the LD converter step, but of course, that's also true for the other steps. So in all of these steps, you have several streams that enter the process and you have several streams that will leave the process. Yeah. Okay. Good. So this is already not super easy to model or to manage the complexity. And just to make things worse, you also do not only have the different streams, but you also have different physical mechanisms that you, if you really want to model this, that you have to describe. You have the thermodynamics, of course. This is what you're using our tools already for. But then you also have to think about kinetics of reactions and also kinetics of mass transport and heat transport. And as soon as we talk about transport, it's clear that you also need to think about space and time. So you need to have some space discretization and time discretization that you describe here. So you have 4 incoming streams, you have 3 outgoing streams, and you have essentially 4 different mechanisms that you have to treat. And luckily, because otherwise life would be boring, the same is true for the other processes as well, right? For each of these processes, you have to analyze, you have to have a domain knowledge on what of these things can we abstract away, what of these things do we have to describe these mechanisms for the different processes. Okay, depending on what your answer is for your domain and for your specific process that you're interested in, you might want to use a different tool. And the idea of FactFlow is that if you are rather confident that you can abstract away most of the kinetic parts, and you just want to have a global flow sheet, then FactFlow will be the right tool to do that. So you only manage essentially the flow of materials from one processing step to the other, while always assuming an equilibrium. Yeah? The FactProSim, on the other hand, is a very nice tool if you want to look into the complexity of the processes in one individual process. So if you want to treat in an effective manner, not in the most detailed manner, but in an effective manner, the heat and mass transfer, the reaction kinetics, and of course the thermodynamics, then FactProSim is the right tool to do that. And finally, if you're real brave and you have a bit of you also want to implement mass transport models, heat transport models yourself, coding wise in Python, then ChemApp for Python is a perfect tool to do this, and it gives you the largest flexibility in the end to also connect all of these different steps into one single program that you then write yourself and manage yourself. And we also will demo that, how easy it is to do this today. It sounds super complicated, but it is not as bad as it was a couple of years ago. All right, now just a short overview of the different abilities or the different aspects of the different programs or modules. We have discussed, and we had a couple of fights about this slide. How do we communicate that? How do we make that understandable for you? What are the categories even that you should care about when you think about what is the right tool for you? And the first one is, do you need to have any programming knowledge? And there are 3 tools, so FactSage, Equilib, the FactFlow, and the FactProSim add-on. None of these really require you to have any programming knowledge. For ChemApp, you do need some programming knowledge. As already indicated earlier, we have a nice training course for that to get you jump-started. And this is not super difficult anymore compared to how it was a couple of years ago also. Powerful for advanced use. Equilib is, you can do quite advanced things with Equilib, but if you really think about process modeling, then Equilib is not the right tool. You will have limitations that you will notice. FactFlow, if you want to have a process flow sheet, yeah, great, but real process modeling, advanced use, requires you to also think about heat and mass transport and reaction kinetics, and then you should either go to FactProSim, which would give you already quite a number of different options and possibilities, or if you just want to have all options and possibilities, then you should go to ChemApp for Python. Model visualization, we will see tomorrow that this is even the way you approach the whole model setup, both in FactFlow and FactProSim, which are really nice ways of starting this. In ChemApp, we will show you that this is indirectly available, meaning you program first, then you can visualize with tools like LLMs. This is maybe maybe we would even or we can even revise this next year. Let's see. Results visualization, that is something that is directly integrated both in Equilib and FactFlow. In FactProSim, it is indirectly available, but also in a very nice way available. In ChemApp also, you can use all the plotting routines in Python, so you also can do that. Support for iterative processes. So if you have recycling streams, some output stream of one process going back to the initial states, or you want to loop over some input amounts, then that is something you can do in FactProSim, and you can do, of course, with highest flexibility in ChemApp for Python. And then finally, scalability, also as Florian already indicated earlier. If you really want to build something that you can scale up, then ChemApp for Python is a very nice tool to do that. Okay. All right, then I want to just to get everybody on board, do a short demo on using Equilib. I have a short script here, as you see in the lower left corner, also for myself. I want to introduce a couple of concepts that are important for you to understand and to know before we go into the demonstrations tomorrow. Yeah. All right, good. So my script says, bullet point number 1, explain inputs, explain streams. Okay, good. Let me do this, right? Okay, thank you, Bitdefender. Yeah, so this is the reactant screen in Equilib that you probably all of you know. As you see, I have already input amounts. So we have iron, we have the carbon, the silicon, manganese, phosphorus, and sulfur. All of them I have input here as stream number 1. So you see already, okay, this is with initial conditions. So I have defined one stream as one single stream, my pig iron. Yeah. Some composition is already indicated here. Yeah, but that's essentially my first stream. You also see that I do not only, if I think about streams, may not only specify compositions, but I must also specify what phase are we in. Yeah, so I could change here my iron reference state from liquid iron to BCC iron at 39 degrees Celsius, which would have, of course, enormous effects if I care about heat balances. Yeah. Okay, good. So it's really important that if you have streams, then you also have to think about phases. Yeah. Okay, then we have a second stream here. Stream number 2 is at 25 degrees Celsius, and this is oxygen gas. Yeah. Okay, of course, in a converter, as I indicated earlier, we blow oxygen into the liquid melt. Then we have one more stream here, 18 tons of iron. That is a poor man's scrap or DRI, whatever, ignoring all of the impurities. Yeah? And then here we have the CaO, so lime that's added, let's say 1 ton per 100 ton of pig iron. Good. Yeah, then you go here to next and you come to the main menu screen of Equilib and you have to do a couple of things. First of all, you have to select phases, and I'm using here a beta version of the latest GTOx. So you see here GT43 is the database I'm using. I have selected all the gas phase species. I've selected all the solid species, and I have also selected all of the solution phases. There's this shortcut here to select all solution phases. You see there is a slick phase. There's no liquid metal, liquid slag, liquid salt, or whatsoever. There's only a single liquid phase. And we will see later that this is automatically forming then a slag and a liquid metal. Yeah. So with GTOx, it's always super important for us that we enable you to always select all phases. You should not have the burden to think about phase selection if you want to do an equilibrium calculation. Only if you want to go beyond equilibrium, so you want to assume that some phase cannot form because of some kinetic constraint, then of course you should modify it, but if not, use standard selection. Okay, then I assume here a final temperature of 69 degrees Celsius in the converter and a pressure of 1 bar. Okay. If you want to use FactFlow, FactProSim, or ChemApp in the future, then you have to do one thing, which is you have to set up your database from the FactSage databases, and then you have to go to File, and ChemSage file, and then export as transparent CST. So that will give you the CST file that Florian also mentioned earlier. And then that is an encrypted excerpt of the databases that you have used initially, and then you can use the other three modules. Yeah. Okay, just that you've heard about it already. That will be needed tomorrow again. All right, good. And then now comes the one feature. When I'm teaching, I always sneak this in because I usually then get a reaction of, "Wow, this is possible. This is really nice." It's a very small thing, and you don't expect it where it is. Okay. For gases, I always love to input gases in moles and not in tons because then you have an easier way to convert between cubic norm meters and amounts. Yeah. So mixed unit input. Mixed unit input is really cool. You can do mixed unit input. You can just write here, I don't know, 20 mole. That's acceptable. So all of the other amounts are in tons and only the oxygen is now in moles. Okay, nice, neat, yeah. But I know that 10 tons is too much for the converter here, but it is the relevant range. Yeah. So there is another nice option. I can right click here and we can talk about whether user experience that is the best way to do it. But you have then a couple of things here. For example, convert this reactant amount to mole. Who knew this feature? Okay, okay. Not everybody. Yeah, and it's really nice. As soon as you do gas plus condensed, I love it. Okay, good. So that was the one thing where I think maybe I have taught many of you or some of you something new. All right, good. Then make oxygen amount variable. I think that should be known already. You can make here, you can add the A in the brackets, smaller sign, larger sign. And you can also do this even with a mole. So you have here, what is it? 31. No, 312,511.7 alpha moles of oxygen. And we all know this was 10 tons. Yeah. Okay, good. Now we have one amount variable. A variable amount. Good. Let's go here to the, now we go to the Equilib screen, and now we add here 0, 1 in steps of 0.1. So now we add 0 to 10 tons of oxygen, but we input an amount of mole. Maybe not the best case to demonstrate this feature, but anyways. And then we can press calculate, and you will see that we perform the calculations, and we get now in each of these steps, we will see the results. You can, of course, analyze the results. You see here in the header, that was our input, and then you always will find the gas phase first. And then you find this slick hash 1, that is the liquid metal. We can scroll down, you will see the exact amounts here in this area. Sorry. And then we have here the slick hash 2, which is not stable. All of the amounts are 0. And if we scroll down further, we see that we form a solid solution phase, the C2S C3P phase, yeah, in some amounts. Yeah, okay. Of course, we want to make plots. So let us just quickly plot this, plot results. Okay, what do we plot? Let's plot weight % of solution species against our alpha variable, and I will select the elements in slick hash 1, which is our liquid metal phase. No, nope, wrong table. To go down further, sorry. Good. Manganese, calcium. I use a larger mouse cursor, which is confusing for me. Yeah, good. Okay. And there we have our plot where we can see the evolution of the different species over the amount variable alpha. So that is the amount of oxygen that we blow into the hot metal. You can see this line is the carbon, how that is going down, how the manganese is going down, how the silicon is going down, and then the phosphorus, which is stable, and only at a later point in time you actually manage to dephosphorize the steel. Yeah. Okay. You can, of course, also plot other things. You can plot what are the stable phases against the amounts variable. You can also plot, because we had the question regarding enthalpy, enthalpies before and heat capacities before. You can plot the enthalpy so the enthalpy change versus alpha. Now, again, maybe one nice feature here, you see that the axis here is really bad, right? I had as an unit for energy, joule has been used, but then we're talking about 100 tons of metal, so of course the numbers are extremely large. There is one nice feature that is here in the edit change scale. If you go there, you can do modifications to your scale to make nicer plots. And I always love this one, E minus 6. So I would just scale down the enthalpy axis. I have now just divided this by 10 to the power 6. So I just have to change here, unfortunately manually, the unit axis to megajoule rather than joule. And finally, we have a plot which looks maybe nicer. Yeah, and that makes sense. We have started with 1300 degrees C liquid metal, and we have 1 ton of CaO, 18 tons of cooling scrap. If we have as final conditions 1600 degrees Celsius without blowing any oxygen in, of course, you need to give heat to the system. So we have a positive delta H. But as you blow in the oxygen, the more oxygen you blow in, the more heat you produce and you release by the burning of carbon and then also the metals. And therefore, you then have an exothermal process as soon as you blow in a bit more. Yeah. Okay, so that was essentially the quick demonstration part I wanted to do. And I want to give you a couple of takeaway items now. There are 3 key learnings, and that will be quite important tomorrow for ChemApp, for that discussion. What are we doing conceptually here is that we have several streams, they enter one reactor, and the reactor will then equilibrate and we get a result. And the result is, as you have here in Equilib, as you have seen here, this is the result. The result contains all of the phases that form. Yeah, we have a gas phase here, we have a liquid metal, and we have I don't know, the C2S C3P. Yeah, so for this to happen, you need to analyze the results, and then you can create new outgoing streams out of the process. Yeah, so streams going in, you get results, you create outgoing streams. Okay. Navigation chemical space is far from trivial. I, of course, had to put this in. Yeah. Okay. There are a couple of challenges, and I just want to name a few here. In practice, you do not only want, in practice, you don't know the exact temperature very often. I mean, temperature measurements in LD converter are rare, I think, while during the blowing process. Also, you probably do not only want to do this for one given composition, but you want to do this for several different compositions. You have not only one hot metal composition that you will always get as an input in practice, but you want to be able to do what I've just done for various input streams. Ideally, if we think about the whole process sheet, you would probably adapt your process depending on your input. If you have a raw metal that is high in phosphorus, you will probably want to add more calcium oxide to the converter in order to remove the phosphorus from the steel, right? So in practice, you are optimizing. And if you want to model such a process, you probably also would be happy if you can optimize this. Yeah. So in this case, optimize maybe temperature, cooling scrap, or calcium oxide amounts. Also, one more thing, be careful with phase selection when splitting reactor results into streams. You have seen in the example that we formed solid C2S-C3P for larger amounts of oxygen addition. You also form liquid slag, of course. If you want to write down rules, and you have to do this if you want to do process flow sheeting, you have to write down rules. And that means you have to be careful. What is named here slag probably is not only a liquid slag, but it might also contain solid oxides. Yeah. Okay, and we will see that tomorrow already in the FactFlow presentation. That is a complexity that we have to deal with, unfortunately. And then, of course, you also always have to think about and have to be sure that you have the answer to the question whether you have dealt appropriately with the detailed mechanisms that are active in your process concerning kinetics, heat transport, mass transport, and also that is something that you will see tomorrow again. Yeah. Okay, that was, I think, what I wanted to demonstrate today, just also to ensure that you will come again tomorrow, because tomorrow will be much more exciting than this part. Do you have any questions or comments?